So let's take a look at, this is chapter 3.1. I wonder if these are numbered sequentially to the end or they're going to restart. They're going to restart. So I need for chapter 3 here. Ready, number 1. Here we go. All right. Oh, I'm going to need this. Naturally occurring copper. Okay. Exists in 2 isotopic forms. Got copper, is it 63 and 65? 63 and 65. Right. So what's the difference between those two? Number of neutrons. This one has 2 more neutrons than that one. You don't have to know that to solve the problem. I just thought I'd throw it in. The atomic mass of copper is 63.55 atomic mass units. So the combination of these two is 63.55 atomic mass units. All right. So the question is, what's the natural abundance of this one? All right. What factor do we multiply that by when we do the weighted average, right? Because this is the weighted average. So what do we have to, we need a value here, something here, and something here that adds together to that one. How do we get to these values? We get to those values by the natural abundance, and I'm going to use the decimal equivalents. Rather than percent, it's going to be 0 point something. I'm going to let that be X. And that's times, we have to assume for the purpose of this problem that the mass of this copper is 63 and the mass of that was 65. I mean, we know it's a fractional value because which one is the only one with a single number and infinite zeros? Carbon. The standard is the only one that's 12.000. Now, the rest of them are all based on that, so they're going to be fractionals. But for the purpose of this problem, we're going to let this one be X. That means this one is 1 minus X. Its natural abundance would be that fraction subtracted from 1. If we're saying that those are the only two, then this one has to be what's left over. Okay. All right. So now this one's going to be 63 and this one's going to be 65. And at least these two, add them together. So this one plus that, because it gives a value here and a value here, is equal to this one. So what we're saying is 63x plus 65 times 1 minus x equals 63.55. Okay. That's our algebraic expression to solve this problem. Right, so this one's 63x and this one's 65 times 1 and then minus 65x equals 63.55. And then we get all the x's on one side and all the numbers on the other side. All right, so let's see, this would be 63 minus 65 is minus 2x. And then we say 63.55 minus 65, which would be what? 1.45 minus, is that right? Take this one, that one together, 1 would be 4. Yeah, that's right. So far, so good. So both sides are negative. So we can say x equals 1.45 divided by 2. All right, because if this is negative and that's negative, same as positive, positive. Okay. All right, so 2 into 1.45 is what? It's 0.725. Is it? Yeah. I think that's right. Isn't it? Okay, so the natural abundance is about 73%. Right, this fractional equivalence of percent would be about 73. And the nearest value you have in that list is 70%. That's why the answer is C. So when you have unique values for each one, and you don't have the squirrely ones like 2 of the above or none of the above and that type of thing, then you look down there and find the best answer, and the best one, the closest one, is 70%. Okay. All right, that's number 1. Found them? Was awful quick. Do they have to do something first?
Well, I got this weird grant and I didn't know what it's for, and then she took that back and gave me some.
Oh, okay. So it's
But-
unique to your universe.
Yeah.
Okay. All right, number 3. The average mass of carbon atom is 12.011. 12.011 atomic mass units. By the way, just as a check, if we took naturally occurring carbon and chopped it down till we kept dividing until we just got one atom, what are the chances that atom would have this mass? 0. Yeah, that's right. Because this is a weighted average of all of them. Okay, assuming you were able to pick up only one. Oh, that's the question. I thought I was being smart. So you answer the question. The question is 0%. The chances of finding one atom with that mass is 0. It will not happen. Yeah, number 4. Okay, what's the mass of 4 atoms of copper in grams? So we're starting from 4 atoms of copper. We want to end up with grams of copper for those 4 atoms. So this is a dimensional analysis problem. It's in a chemistry course, but it's really a math problem. We want to go from atoms to grams, but we don't have a direct conversion factor from atoms to grams. It doesn't exist. So if you work backwards, you say, how are you going to get grams in the top so it'll be over here? And what goes down here? Well, we do know the relationship of grams to moles. 1 mole for copper is 63.55 grams per mole. Okay. So how about moles over here? Moles would have to be on top, wouldn't it, to cancel out? Because we don't want moles hanging around over there. Right? What goes down here? Yeah, atoms, that's right. 6.022 times 10 to the 23rd atoms per mole. Avogadro's number. So now all we have to do is, that's the thinking part. The rest is number crunching. And if we crunch the numbers correctly, it should come out to 4.22 times 10 to the minus 27 grams. And that's the mass of 4 atoms of copper.
So you would divide the 4 by the Avogadro's number and then times that answer by the 63
Correct.
to get the 4. Okay, I just wanted to make sure.
Exactly right. In fact, you can do it in any order you want. You can do 4 times 1 times 63 and then divide by this. Or you can do this divided by that times that. It doesn't matter.
Okay.
But it works all the way through. That's 4. Let's see who's next. 6. You got a sample of zinc and a sample of aluminum. Okay. Zinc and aluminum samples. Equal number of atoms in each one. So this has X moles, and this has X moles, exactly the same number. Which of the following statements concerning the masses of the samples are equal? So we're looking at mass of zinc and mass of aluminum. Now, we don't know that. But we can compare by ratio. If the number of moles are equal, the same number of moles, let's just, for argument's sake, let's say it's 1 mole. What would the mass be for zinc? Mass would be 6538. Right? 6538 grams. Aluminum would be 2698. If it was 1 mole, right? If they were both 2 moles, it'd just be double that. So for the purpose of comparison, this should work. Which of the following statements concerning? Okay, A, the mass of the zinc sample, mass of the zinc, is more than twice as great as the mass of aluminum. Yeah, twice the aluminum will be a little less than 60. 65 is more than twice that. Right, so we found our answer. We could look at all the rest of them, but that would just eat up time. That statement is correct. All right. 7. A sample of ammonia has a mass of 43.5 grams. And so what's ammonia? It didn't give you the formula. Okay, so if that happens on a test, just ask me and I'll tell you what ammonia is. It's NH3. So when you use anybody still use ammonia at home to clean? Or is it, they use things that are mixed up and have ammonia in it? Probably. It does.
It smells terrible.
Yeah, you know the smell of ammonia. That's what it is right there.
We use it to burn patients' back.
Yeah, exactly. Smelling salts.
Yeah, it's right there.
Yeah, there are lots of uses for ammonia. Actually, now a lot of the ammonia-based cleaning products are quaternary ammonias. So we would start off with this. Quaternary means 4. And then we would substitute for each one of those hydrogens. So we'd have this, and we'd have something out here, we'd have something out here. And usually it's a carbon-based side chain. And 2, 3, and 4. And it probably would have a plus charge. But this is less noxious and it works just as well. In fact, I've got the glass cleaner that I use called Micro 90 to clean up the mess that y'all make. Is a quaternary ammonium compound. Anyway, let's get back to the question. So with that one, we have 43.5 grams of this sample. Right? How many molecules are in this sample? Okay, if we have that many grams, we can determine how many moles, right? Because all we need is the molar mass of ammonia. Right? Nitrogen is 14.01. And then 3 hydrogens is 3.03, correct? So 17.04 is that many grams per mole of that compound. Okay. That gives us moles. We're going to ask for molecules. So remember, moles is just a number. 6.022 times 10 to the 23rd things. It can be atoms, ions, molecules, chickens, whatever. Doesn't matter. It's still just a number. So we cancel the grams, numerator, denominator. Now we're going to cancel the moles and leave us with molecules. All we need is the conversion factor. Right? So that leaves us with molecules. Now all we have to do is crunch the numbers. This one times that one divided by this one. And it should come out to 1.54. 54 times 10 to the 24th molecule of ammonia. We use ammonia in agriculture too. You've heard of nitrogen fertilizers. If you look at a bag of fertilizer at a feed store, it'll have 3 numbers on it. First one is nitrogen, the percent nitrogen by mass. But if you use ammonia, what we call anhydrous ammonia, that is, it's pure, no water, no nothing else, and you have to use special equipment to handle it, then you can put, and you have to have stainless steel knives that go under the ground to inject it, because it's a gas, and you want it to react with the moisture in the ground so it'll stay put. Right? If you just blow it on top of the ground, it'll go, it's gone. So you inject it into the bottom, and it's 100%. I mean, it's not a fraction. Like ammonium nitrate's 34% nitrogen. Urea, right? They use that sometimes. It's 46%. Right? But this is 100%. So if you've got the equipment, and it's dirt cheap, right? So farmers that have huge acreages, I mean, I'm talking about thousands of acres, then they may use that. It might be economical to use ammonia instead. Now, that doesn't give you the other nutrients that you want, like the 3 numbers in phosphorus and potassium. Doesn't give you phosphorus, doesn't give you potassium, so you have to do that a different way. Anyway, that was all free information there. Let's see, 8. How many moles of hydrogen sulfide are contained in 49.7 grams? 49.7 grams of hydrogen sulfide. And we want to know how many moles does that represent? This is fairly simple. This is a 1-step process. You just need the molar mass of that 2.02 for the hydrogens. The sulfur is 3207. That's 904. So 34.09 will cancel the grams and leave you with moles. And that should be, right, if we estimate it's like 1.3 or 4, so 1.46. By estimating that value, I know that if I actually calculated it, I know I should be right. Just does it make sense? If I can estimate the value, then my calculator's going to spit out, garbage in, garbage out. If you put the right numbers in, you get the right value. If you put the wrong numbers in and do the wrong operation, you get the wrong value. But if you estimate it, then you can keep your calculator honest. Okay, that was B. Let's see, number 10. For which compound does 0.256 mole weigh 12.8 grams? All right, so let's find out what its molar mass, what the actual molar mass is that they've given us. 12.8 grams per 0.256 moles. Okay. So that value is going to be 12.8 divided by 0.256 is 50. That's 50 grams per mole. Now we got to find out which one of those matches that. A, B, C, D, and E is none of these. E is none. All right, so we got to look at each one until we find, at least find the one that's right. C2H4, H4O, CO2, CH3Cl, and C2H6. Okay, This one would be 2 times 12.01. 24.02. Plus 4.04 plus 16 for oxygen. All right, is that even close? 24 would be 28. Would be 34, around 34. All right, so that's not it. We didn't have to use our calculator. This one was 12.01 plus 2 times 16 is 32. All right, so that's 44. That ain't it. How about this one? 12.01 plus 3.03 for the hydrogens plus 35.45 for the chlorine. All right, so that's 1504. That's 50.49. That's pretty close. I hang on to that one. And this one is only, let's see, 2402 for the 2 carbons plus 6.06 would be about 30, approximately 30. So that was not it. All right, so we found the one that's the best answer, this one right here. C. Now, if you claim none of these because it's missing those last 2 edges, then you just have to show me. Prove you did the work and say, okay, I give you credit for it. Otherwise, just mark the best one and move on. Number 10. And 11. Okay. Calculate the molar mass of barium sulfite. All right. You got to be able to write the compound. So barium is this, right? Is that a type 1, type 2, or type 3? It's not a type 3 because that's a metal. Okay, where does barium come from? Right. All of those alkaline earths are +2 charge. Right? +1, +2, +3. And then +1, +2, +2. Those are the only ones that are fixed. So this is a type 1 compound with a 2+ charge, and then sulfite. That's not up there. That's a polyatomic. So you look it up in your table, and you find it's SO3 2-. And so one of each is all you need to balance the charge. So there's your formula. So the molar mass of barium sulfite, see, barium's a big one, 137.33. 137.33. And sulfur's 3207. 3207. And then 3 oxygens. What's 3 times 16? 48. Okay, so 7 and 3 is 10, carry the 1, there's a 4, and there's 10, 17, carry the 1, let's see. 6, 10, 11, 217, 40. Is that up there? Yeah, E. Okay. It takes practice. You got to do a lot of them. Like I said before, 2 best friends, curiosity. What's the other one? Boredom. If you get bored working these problems, then you know them pretty good. All right, 11, 13. Let's see. What's the mass of 6.761 moles? 6.761 moles of what? Sodium hydroxide. There's sodium, right? What's hydroxide? It's a polyatomic. OH minus. Sodium's an alkali metal, so it's +1 always. Hydroxyl is fixed at -1 because it's a polyatomic and their charges are chiseled in stone. All right, so we want to convert that to mass. All right, we need moles on the bottom, mass on the top. So we cancel the moles. So what's the value? Well, sodium is 23 3.00 to two decimal places. Oxygen 16 and hydrogen's 1.01. All right, so that's 1, 0, 7, and 40.01. Times 6.761. And if I do the math right, it should be 270.4 grams. Let's see if that makes sense. 7 times, if we round this up to 7, that'd be 280. If we kept it at 6, that'd be 240. So it's between those two. Looks reasonable. All right, that was 13. And let's scroll down to, oh, there's ammonia. Stuck it in there. 15. One molecule of a compound weighs 2.93 times 10 to the minus 22 grams. For that molecule, the molar mass of the compound is. All right, if this is one molecule, this is per molecule, what we want is a mole of molecules. Right? We want to change this part to moles. We want to keep that part, right? Because molar mass is grams per mole. So this is one molecule. We want to change that. Molecules per mole, and we know the magic number. 6.022 times 10 to the 23rd. Okay. So keep grams, cancel molecules, and leaves us with grams per mole. And if we multiply it correctly, we should get 176 grams per mole. Okay. If I make this round that off to 3, round this one off to 6, then that would be what, 18? And then 10 to the minus 22 and 10 to the 23rd is 10 to the 1st, right? So this would be times 10. Right? That'd be 180, would be my estimate, right? So I'm good. I feel confident that my calculator didn't stab me in the back.
How are you getting the 6.002 times 10?
6.022, that's Avogadro's number. Yep. Is I don't know if it's in the. Did I put it in useful information? Should have. Okay, I guess I expect you to memorize it. Avogadro's number. He didn't discover it. It was just named after him. All right, 17. Compound is composed of element X and hydrogen. X and hydrogen. Okay, so far, analysis shows the compound to be 80% X by mass. It's 80% X with 3 times as many hydrogen atoms as X atoms. So that means we have 3 times that, 3 there, 1 there, per molecule. And so that is the molecule. If this is 80%, which element is element X? All right. So if this is 80% X, how much is the hydrogen? 20%, right? It has to be. 3 hydrogen atoms are 20% of that molecule. Okay. Well, let's assume, for argument's sake, I think I'm doing this right. I'm not barking up the wrong tree. if we say that this whole molecule, let's say we have 100 grams. If we have 100 grams. Yeah, if we have 100 grams, how much of it is hydrogen? 20 grams, right? 20 grams is hydrogen. This is a gram sample. Then 20 grams of it is hydrogen. So we can calculate how many moles of hydrogen that is. All we need is our molar mass for hydrogen. 1.01. So we divide 1.01 into 20. You know, if we were quick about it, we just say 1 and say it's 20 grams, which would probably work. But I got 19.8 moles of hydrogen. Okay, what's the ratio here? The ratio is 3 to 1. So for every 3 moles of hydrogen, you have 1 mole of X. Correct? That's the ratio, 3 to 1. So that means 3 into 19.8, 19.8 is 6.6. So this is 6.6 moles of X in that sample. Well, how much does X weigh? If 20 grams of it is hydrogen, that means 80 grams is X. So that many grams for 6.6 moles should give us the molar mass. .12 12.1 grams per mole. Right. Within experimental error, you can find elements up here if you know their molar mass. Usually. Right, there's 12.01, so closest to that one is carbon. That's what I would say. I guess carbon. Okay. Now I bet if we had made this 1 and made that bigger, that would have made this bigger, and this being bigger would have made that smaller. It would have come closer to 12.01 if we'd used 1 instead of 1.01. Okay. 18. Okay, 18. Which compound contains the highest percent by mass of hydrogen? Okay, it's gonna take some work. A, B, C, D, and E. All right, so we've got HCl, H2O, H2SO4, hydrogen sulfide, and hydrofluoric. Okay, we want the percent by mass of hydrogen. Remember the calculation of percentage by mass. You need the total mass of a mole of the compound, and then the mass of the element that you're interested in. So we're going to do Henry Ford again. Do each one exactly the same way, only they're different numbers. Right? So HCl would be 1.01 plus 3545. And then let's see, hydrogen, yes, 1.01. Oh, I forgot to multiply times 100, each one of them. To give you percent. Okay. All right, so that'd be the percent for this one. How about water? What's the total water? Remember that one, 18.02. Hydrogen's going to be 2 times 1.01, because you got 2 of them per mole. Let's see, how about this one? 2 times 1.01 for hydrogen plus sulfur, which is 3207. And 4 times 16 for oxygen. And the hydrogen's going to be up here, 1.01, like that. Okay. And we got 2 hydrogens for this one also. And 2 hydrogens here because it's part of the total. And then sulfur is 32.07. And then HF. So we have 1.01 on top, 1.01 on the bottom, plus fluorine, which is 19. There we go. So that'll give us the values and tell us which one has the highest percentage by mass of hydrogen. All right, so 1.01 and 35.45 is in the denominator, 3646, and 1.01 in the numerator. Divide is 2.77%. Hydrogen by mass. Okay, how about water? Well, let's see, it has, we already calculated the bottom part, so it's 2.02 divided by 18.02 times 100 is 11.2%. And 11.21%. Okay. Now, this one's going to take some work. 2.02, 32.07 for the sulfur, and 64 for the oxygens. Okay, then 2.02 divided by that value is 5.92%. Hydrogen. Okay, got 2 more to go. 2.02 plus 32.07. And then divide that into 2.02. And that's 5.93. 5.93. Oh, wait a minute. Did I do that right? Let me do that again. 2.02, 32.07, 2. Yeah, 5.93. That can't be right. No, this is not right. See, because I got more in the denominator here than I do there. That's wrong. Somebody should have caught me on that one. Yeah, 206. There we go. They just, if you're always thinking, does it make sense? If you got these 2 different formulas and you get the same percent hydrogen, can't be right. It's got to be wrong. Okay, and then this one is 20.01 in the bottom. And then 1.01 on the top. I get 5.05. Okay. So we're looking for the highest percentage. That's water. B. It's a lot of work for just one little answer. That's where Henry Ford comes in. Uh, 19. All right, a substance contains 35 grams of nitrogen. Yeah, what we know, 35.0 grams of nitrogen, correct? Yeah, 5.05 grams of hydrogen. 60 grams of oxygen, 60.0 grams of oxygen. Okay. Now, this compound, remember the law of definite proportions. those ratios, that grams, that grams, that grams, that ratio is fixed for that compound. No matter where you find it or how much of it you have, the ratio of those is fixed. So let's see, out of that, we have a total of what? Let's see, 5, 0. Carry the 1, 100.05 grams. Okay, of that sample. Now, if we have 153 grams of the sample, instead, the question is, how many grams of hydrogen do we have? What's the ratio? Well, the ratio to the whole is 5 to 100, or 5%, 0.05 is the hydrogen. So if we multiply that times 153, we should get, let's see, 100 would be 1.5, 3, and then times 5, 15, 1.5, 6, 5, 7. That should be 7.65. 7.72, close enough. Because I rounded off. I rounded off here and I rounded off there.
Are you getting these too?
I'm saying that's the fractional amount of hydrogen to the total. Right. Actually, it would be 5.05 divided by 100.05. So that's 0.05047. And we multiply that times 153. Let's see if it gets us any closer. 7.72. There it is. If you do the exact calculation, see the ratio of each one of these to the total is the same idea as the ratio of one to the other, right? It's fixed for that compound. So if we know the ratio, the fractional amount of hydrogen per this amount, then it's the same fractional amount of this one. So this value over here should be ratioed to that the same way this one is ratioed to that one. That's what I did here. Right? That's the ratio of hydrogen to this amount. So the same ratio should be to this amount, and that gives us 7.72 grams. And all you have to do is take 7.72 divided by this, should be equal to that one divided by that one. Okay, now it's 19. $22. Okay, each molecule of testosterone contains 19 atoms of carbon. 19 carbons. The mass percent of carbon in testosterone is 79.12%. 79.12% carbon. Okay. What's the molar mass of testosterone? Let's see. What do we have to go on here? 19 atoms of carbon would weigh what? We can do that. 19 atoms of carbon. Let's see, atoms. What's the magic number here?
0, the 6.3.
2 times 10 to the 23rd.
Yeah.
Okay, so that would give us the moles of carbon, and then we can convert moles to grams, right? And carbon would be 12.01. So that'll give us with 19 atoms, that tells us the mass of carbon in that compound. 19, 6.022, x 1.3, divide, and then 12.1 times. So this is 3.79 times 10 to the minus 22 grams of carbon in that compound. And that compound is 79.12% is carbon. Right, so 3.79 times 10 to the minus 22 grams of carbon is equal to the total mass, and this is per molecule. Right, that's per molecule. So this per molecule is equal to the mass of the molecule in grams times the percentage of carbon. This is how much carbon is in that molecule. This is the percent of that value. So the total mass of the molecule times 0.7912 is how we got this value. That's the total mass of the molecule. This is how much is carbon, and this is how much is carbon. So we can solve for X. We can say X is this number divided by that number. 0.7912. So X equals 4.79 times 10 to the minus 22 grams per molecule. Right, for testosterone. Now we just need to convert this to moles. Grams per mole is molar mass, and that was the question. So how do we do that? We need 6.022 times 10 to the 23rd molecules per mole. So this number times 6.022 10 to the 23rd is 288 grams per mole. E. Okay. There's probably an easier way to get there, but that's the way I was
Well,
headed.
you kind of lost me at. All right, so I got the top part.
That makes sense.
Yeah.
Okay.
So you lost me down here whenever you done the 79% and so you just convert the 79% to a decimal and then
Fraction.
you divide.
Yeah, well, I said yes. This is the value of carbon. That's how much is in the molecule. One molecule. And this is how you got that value. The total mass of the molecule times how much of it is carbon is this value. And then I just solve for X.
Okay, so 3.79 times 10 to the negative 27.
Yeah, this has to go
Divide
like that. And this goes over here.
it. Okay,
And that's where this one came
and
from.
then you get that number and then you do that to get your grams per mole. I
Right.
got that. And you just lost me in the middle there. I got it.
Okay. Now it's 22. $24. I think I'm going to run out of time. As usual. An oxide of iron has the formula Fe3O4. Now that's a true ratio of iron to oxygen, but you're going to be hard pressed to find a whole number charge in here to balance that equation. Right. Oxygen's usually -2. So that'd be -8 total, wouldn't it? So that means +8 for iron spread over 3 irons. Right, so that's 2 2/3 plus charge. 2 2/3 plus. Right. So what we think really is happening in the crystal structure here, we've got Fe2O3 and we have FeO. That's the 3 irons and the 1 oxygen. And this one will give you a whole number charge for iron, and this will give you a whole number charge for iron. But that's true ratio. It's just
it doesn't behave. But we can still use it to solve the problem. Let's see, what mass percent of iron does it contain?
All right, so all we have to do is say, all right, mass percent is equal to 3 times iron, which is 5585. 85 in the numerator, and then 3 times 5585 in the denominator, right? Because we didn't throw it away just because we put it up here. And then 4 times 16 times 100. If we do our calculations correct, it should be 72%. This thing's given out already. Okay. Over there.
Okay.
Yeah, sometimes you have to go off-site to get your information. And that usually ends up in the, that's iron, yes. 3 irons in the numerator and 3 irons in the denominator, because this has to be the total mass of a mole of the compound. So you have it up here and you have it down here. And then extra, whatever is extra in the molecule is oxygen.
Cause that's the whole of
Mhm.
the compound itself.
This is the whole compound. This is just the element you're interested in.
Got it. And you times it by 100 to get the percent.
Uh-huh.
Got it.
Yep. All right, 24, 26. Ammonium chromate. Oh, isn't that nice? They gave you the formula. Contains what percent nitrogen by mass? So ammonium chromate, right? Yep. Okay, so for this one, it's just 2 times nitrogen, 2 times 14.01. And then we put that in the denominator too, 14.01. And then how many hydrogens? We have 8 hydrogens. Right, and then we have 1 chromium, which is 5200, rounded to 2 places. And then oxygen 4 times 16. There you go. Times 100. Right. And if we do the calculation correct, that should be 18.4%. Nitrogen. Get another one. These things don't last very long. But they erase better from the board than these things that they buy from us. These expos. They get in there and they want to stay. These, my personal stock erases better. Okay, we good? All right. 26. And 30. A hydrocarbon compound consisting only of carbon and hydrogen. That's what hydrocarbons are. It's found to be 85.6% carbon. 85.6% carbon. What's the empirical formula? All right, if these are the only 2 elements in there, how much hydrogen is there? Right? That should be 100%. If you don't do that, then you're stuck. Next step is to get a mass that you can work with. So if we assume that the sample is 100 grams, that makes this one 85.6 grams, right? Because what does percent mean? Parts per 100. Grams per 100 grams. So if we have a 100-gram sample, we have 85.6 grams of carbon. And we have 14.4 grams of hydrogen. Now we can work with it. We want to convert these to moles. Right, for carbon, it's 12.01. For hydrogen, it's 1.01 a mole. And we get a value for that. 85.6 divided by 12.01
is 7.13. 7.13 moles. Now, this compound, this percent ratio is fixed for that compound. So when we convert these to moles, the mole ratio is fixed too. Let's see, 14.4 divided by 1.01 is 14.3. Okay, that's not a whole number. All right, empirical formulas, molecular formulas must have whole number subscripts. So what do we do to get that fixed? Divide by the smallest one. That's obviously going to be 1. And then 14.3 divided by 7.13 is about 2. So the empirical formula would be 1 carbon, 2 hydrogens. Okay, simplest whole number ratio. That may or may not be the molecule, but it is the empirical formula.
Why?
Oh, because I can't put a fractional number down here. So I want to try to get as close to whole number as possible. And the easiest way is to take the smallest one and divide everything through by it. Because we've established the ratio 7.13 moles to 14.3 moles. That's fixed. So if we do the same thing to each one, multiply it or divide it by the same number, then the ratio is still the same. So if I divide this one by that, I get 1, divide it by that, I get 2. Okay, that was 30. I still right? Good, okay. 32. Let's say the empirical formula for styrene is CH. Right, so the empirical formula is CH for styrene. The molar mass is 104.1. So we need a multiplier here. And once we find that value, the molar mass of this compound is 104.1 grams per mole. Okay. Well, how do we get there? We got to find that value. If this is 1, then whatever this is, 12.01 plus 1.01, right? That's 203, 13.02. If this is 1, it's 13.02. Well, it ain't that. Right? If it's 2, it'd be 26.04. It ain't that either. So the quickest way to get there is to ratio the 2. I call this my empirical mass or empirical weight. And that's the molar mass. That's the true mass per mole of the compound once we find out what the true subscripts are. So if we just ratio the 2, 104.1 divided by 13.02, we'll actually find out what that value is. Let's see. I'm not going to try to do that one in my head. And divided by 13.02. So it's exactly 7.995. We want a whole number. That's so close. That's 8. So if this is equal to 8, then the molecular formula is C8H8. Okay. And if you multiply 8 times 12.01 and 8 times 1.01 and add them together, you should get that value right there, 104. Okay, so the answer is B. Adipic acid. We want to take time to do this one. It's the same procedure, only I'm running out of time. All right. To find the empirical formula, that's very simple. Assume 100 grams That means you got 49 grams of carbon, 43.8 grams of oxygen, and 6.85 grams of hydrogen. Convert them to moles, ratio them, divide by the smallest one, and then work your way to whole numbers. If you divide by the smallest one and you get a fraction, say a 0.33 or a 0.5, those are easy. 0.33, you just multiply all of them by 3. You get rid of the third. If you got a 0.5 in there, multiply by 2, you get rid of the half. Right, and I'm sure that one's in worked problems. So I'm going to skip that because we have to move on. 34 also, vitamin C. That's the same type of thing. In this case, you know the molar mass. Once you find the empirical formula, calculate the empirical weight, divide it into 180 and find out what N is. Then multiply it by your empirical formula. How about 36? Just take time for 36. How many of the following are true concerning balanced chemical equations? Now, let's see. The number of molecules is conserved. Nope. The only thing that's conserved in a balanced equation is the number and type of atoms, of elements on both sides. So 1 is not right. Coefficients for the reactants tell you how much of each reactant you're given. All right, that's a little misleading. When we say how much, we usually mean mass or volume. And it doesn't do that. It tells you how many. 3, atoms are neither created nor destroyed. Yeah, that's true. That hadn't changed. Coefficients indicate the mass ratios. Nope. Mole ratios or molecule ratios. The sum of the coefficients on the reactant side equals the sum of the product side. Nope, not necessarily. If it does, it's purely coincidental. So Roman numeral 3 is the only right one in that bunch. The rest are misleading. 37. In balancing an equation, we change the blank to make the number of atoms on each side of the equation balanced. So once you've got an equation written with the correct compounds in their places, the subscripts of those coefficients, those compounds is fixed. Right? Law of definite proportions. Now, you can't change them. The only way you can balance an equation after that is with coefficients. And that's B, coefficients of the compounds. That's the only way to balance an equation. $39. What's the coefficient for oxygen when the following equation is balanced? All right, so we'll do this one. Ooh, 40 is a stinker. Maybe we ought to do that one too. So we got ammonia. And we've got oxygen. Yields NO2, nitrogen dioxide, plus water. What kind of reaction is that anyway? We went over that, didn't we? It's got oxygen here, this is combustion. And all combustions are redox reactions. We did talk about that, didn't we? Right. Maybe it's in the next chapter. Chapter 4. Let me see. Yeah, we talked about types of reactions. So this is a combustion and a redox reaction. Okay, so let's balance it. You want to use the budget method to get practice. So we got nitrogen, hydrogen, oxygen in here. Take our initial inventory. 1 here, 3 there, and 2 there. See, this is 1, hydrogen's 2, and oxygen's 2, 3. Okay, now where do we start? We don't start with nitrogen, it's already balanced. How about, and we don't start with oxygen because it's an element. We keep it to last. So we start with hydrogen. Okay, we got hydrogen in one place over here and one place over there. What's the trick? Cross multiply. So we'll take this 2 and put it over here. We'll take that 3 and put it over here. That gives us 6 hydrogens there, 6 hydrogens there. Okay, then we have 2 nitrogens here. And let's see, we've messed up the oxygens. So 3, 4, 5 oxygens now. Okay, so now we got to fix nitrogen. On this side, we need 2 nitrogens. I messed up the oxygens again. So that's 4 plus 3 is 7. Now we can fix the oxygens up here. Except what? You got an odd and an even. So the best way to get 7 out of an even is with a fraction. Let's say 7 halves will give us 7 oxygens, correct? Now we got to get rid of that fraction. So how do we do that? Multiply the whole thing through by 2. Right? That gets rid of this half. Right? 2 in the numerator, 2 in the denominator, they cancel, leave us with 7. This one becomes 4. This one becomes 4. This one becomes 6. So coefficient for oxygen is 7. C. Balancing the equation takes lots of practice. I've tried to shorten the learning curve by giving you a method, but you still have to work it out. All right. Let me see if I can do the next one without getting hung up. 40. I don't even have chapter 4 yet, and I'm out of time. The sum of the coefficients for the following equation when balanced. All right, so we got sodium amide, I think that is. Sodium amide. Plus sodium nitrate yields sodium azide plus sodium hydroxide plus ammonia. Okay. If you got a modern car with an airbag in it, it's got that right in it. Sodium azide. All it needs is a little shock, like an electrical kick, and this will decompose into nitrogen gas and sodium something or other. Sodium hydride probably. But it does it in an instant. That's why those bags go like that. Anyway, let's see if we can balance this thing. All right, so we got sodium, nitrogen, hydrogen, and oxygen. Okay, we got 2 sodiums here in 2 different places. We got nitrogen in 2 different places. We got hydrogen in one place, that's good. And we got oxygen over here, 3. Okay, on this side, we've got 1, 2. That we've got 3, 4 hydrogens, nitrogen, excuse me, 4 nitrogens. Then we've got oxygen, 1 oxygen, and we've got 4 hydrogens. Let's see if I did that right. 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 2, 6, 11. 1, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so I counted them all up. That's good. Now, where do we start? Well, we don't have any single elements in there, but we've got nitrogen in 2 places and sodium in 2 places. So we probably want to get those balanced first. All right, sodium's already okay. Nitrogen, how about nitrogen? All right, we got 4 nitrogen on that side, and we need 4 on this side. Well, we got 2 here already. What if we say 2 here? What would that do? Well, that would give us the nitrogens, obviously. That would give us, make 3 sodiums.
And that would give us 6 oxygens. How about hydrogens? Before we jump back up to sodium, let's check out the hydrogens. We got 2 hydrogens there, we've got 3 over there, 4 over there. What if we did 2 here? That would give us 4 hydrogens, wouldn't it? Right, so that would be, and it gives us 2, 4 sodiums. Okay, and that gives us 2 nitrogens here and 2 there, that gives us 4 nitrogens still. And 4 hydrogens and 6 oxygens. Okay, so we're still good, I think. So that's 18. So that's 2, 4, 6, 8, 10, 12, and 6 is 18. That's okay. I didn't miss anything. All right. So we got oxygen and sodium that still need to be met. All right, I've got oxygen in one place here. If we did 6 here, that would unbalance the sodiums. Right. Yeah, I knew this was going to be a bear. All right. Put a 2 here. And a 2 there, that gives us 4 sodiums. If we put a 3 here, that'll give us 3 times 3 is 9 nitrogens. 10 nitrogens. Okay. Four, 6, 7. Okay. I'm gonna have to cheat. How did I work this one out? Number 40. Wrong 40. Here we go. So I went to oxygen first. Then I went to nitrogen.
You said this is gonna be recorded.
Yes. Okay. So let me back up. And do oxygen first. Well, this is gonna be 3. This will be 2 and 2 and 2. 2, 2, 2. And that's still 2, 4. Okay. Do oxygen first. So I need 3 oxygens over here. If I put a 3 there, that gives me 3 oxygens. That gives me 4 sodiums. Okay. That gives me still 3 nitrogens, 4 nitrogens. And hydrogens. That gives me 3 plus 3 is 6 hydrogens. Correct? That'd be 9 and 8, 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 17. Okay. Now, let's keep at those. Oxygens are balanced. If I go to, where did I go next? I went to this one over here. So if I multiply this times 3 plus 1 gives me 4, okay? That gives me 4 here. 3 plus 1 gives me 4 nitrogens. 6 hydrogens.
And that balances. I don't think I'll give you one like that. Unless it's extra credit. Right, if I have to cheat, I can't expect you to get it. All right,
So I'm still in chapter 3 and we're out of time. So if you have to go,
and I'll keep recording until we get all of them done.
If we don't have to leave, we can stay.
Oh, yeah, sure. Right, I don't have a class after this,
How long do you think roughly it will take?
probably another hour. To get through chapter 4,
So we got 2, 3 classes.
yeah, about 3 o'clock.
I'm good.
That's as long as I can stay anyway. I gotta get out of here by then. Okay, when the equation C6H14O2 is balanced to a small set of integers, sum of coefficients. Okay. So let's do
43, this one's fairly tame by comparison. C6H14 is another hydrocarbon that we're gonna burn. That's a combustion. It makes carbon dioxide and water. And so we have carbon, hydrogen, oxygen. 6 carbons, 14 hydrogens and 2 oxygens. And we have 1 carbon, 2 hydrogens and 3 oxygens. And we got that oxygen to hold out. So let's do the carbons first. You have 6 here. That gives us 12, 13 oxygens. Okay, then we'll do hydrogens. You have 14 on this side. We put a 7 here. That gives us 14 hydrogens, but it also gives us 7 plus 12 is 19 oxygens. Then we can use our fraction to give us 19 there, and then we get rid of everything. I mean, we get rid of that fraction by 2. So that gives us 2 there, 19 there, 12 here, and 14 there. So what's the sum? That's 21. That's 33. And that's 47. 47, B. Okay, sum of the coefficients. Yeah, these combustions with hydrocarbons are they're really tame by comparison. All right. We're good? Okay. Or did I go too fast? I get in a hurry sometimes. 44. A reaction occurs between sodium carbonate. Sodium carbonate. This is a -2 and this is a +1, so we need 2 there. Sodium carbonate and hydrochloric acid. Right, and yields what? It yields sodium chloride. Well, they're going to tell us what it is. Sodium chloride, carbon dioxide, and water. Okay. The correct set of coefficients. All right, so we have sodium, carbon, oxygen, hydrogen, and chlorine. See, we can't use carbonate as a balancing group because it loses an oxygen to go here. So we have to separate all the elements. We have 2 here, 1 there, oxygen's 3, hydrogen's 1, chlorine's 1. On this side, we have 1 sodium. We have carbon. We have 1 carbon. Right, yeah, 1 carbon. We have oxygens. We have 3 oxygens. Hydrogens, we have 2. And chlorines, we have 1. All right, so we don't have any single elements. So we just start wherever you want to. Right, we can start with hydrogen or sodium. I go with sodium. We put a 2 here. That makes 2, that gives us 2 chlorines. Okay. Then move down to hydrogens. We got 2 hydrogens over there, we need 2 on this side.
2 hydrogens, and that gives us also 2 chlorines. We're balanced. That's it. So the coefficients are, don't forget, that's a 1. 1, 2, 2, 1, 1. D. D would be the answer. Okay. Uh, 45. Let's scroll it up a little bit. A chemical reaction has the equation 2A plus B yields C. 2A plus B, C. Okay, which of the following figures best illustrates a stoichiometric ratio? When we say a stoichiometric ratio, we're talking about this part of the equation right here. So if there are any C's in there, throw it out. Right, we got any C's in there? Yeah. Roman numeral 4. Roman numeral 4 can't be. Let's see. So what else we have? 2 A's for every 1 B. So let's see. Number 1. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. Yeah. That's 8 to 4. 8 to 4 is 2 to 1. So Roman numeral 1 is true. Okay, so we got that one. How about the next one? Let's see. Next one is 1, 2, 3, 4, 5, 6, 7, 8 A's. That's Roman numeral 1. That's true. Roman numeral 2 is 8 A's and 1, 2, 3, 4, 5, 6, 7, 8 B's. All right, so that one won't work. How about 3? 1, 2, 3, 4, 5, 6, 7, 8 B's and 4 A's. 4 and 8. That one won't either. So Roman numeral 1 is the only one that works as a stoichiometric ratio. For every 2 of these, you need 1 of those. Is when they react, they produce a C and nothing's left over here. And just to reiterate, that's a theoretical situation. In real life, it never happens. 46. 7.11 gram sample of potassium chlorate was decomposed according to the following equation. So you can put potassium chlorate in a vessel and heat it up, and it'll evolve oxygen, and you can run a tube over underwater and catch it, right? See it bubbling out. Or you can put potassium chlorate in solution and dribble it on the floor and let it dry. Then when your lab tech or your professor walks through and steps on it, it'll go pow. The activation energy is just a little bit of pressure is all it needs. And the pow is the oxygen being evolved, right? So it's not dangerous. It just shocks them and everybody gets a giggle. How many moles of oxygen are formed? All right, 7.11 grams. And you have 2 KClO3 yields KCl, 2 of those, plus 3 oxygens. Okay, if you got this many grams, we want to find out how many moles of this one. Moles. So if this is balanced, which it is, we need to convert this to moles. Right. Potassium chlorate. Potassium is 39.10. 39.10 to 2 significant figures, 2 decimal places. Chlorine, 35.45, and 3 oxygens is 48. That's we have 5, 5, 22, carry the 2. So that's, let's see, it's 12. 122.55. So divide that into 7.11. 122.55. We get 5.88. No, 80. Sorry. 0 times 10 to the minus 2 moles
of potassium chlorate. Now we need a conversion factor that will take us to oxygen. Oops. There, sorry about that. That's ozone. We don't want ozone. ClO3. So the ratio is for every 2 of these, you get 3 of those. So 1.5 times that value should give us 8.70 times 10 to the minus 2 moles of O2. That's in standard notation, right? So we moved 2 places. Right? 0870. D.
So you took the 580 and you divided it by the 2, 3.
Yeah, divide by 2 and multiply by 3, which is 1.5. That's how I did it, my calculator.
Just wanted to make sure my
Mhm.
brain was.
Yep. And to watch me, I take shortcuts. Especially when I'm pressed for time. All right, 47. How many grams of calcium nitrate can be produced by reacting excess nitric acid with 6.33 grams of calcium hydroxide? So we got calcium hydroxide. Like the way we read that is calcium hydroxide plus nitric acid. That's going to be aqueous, of course. And I'm not sure about that one. But we have 6.33 grams of this. And we have excess here. Okay. So this is limiting. All of that's going to be used up and produce calcium nitrate. Now, that's not balanced. What are we missing? Hydrogens. Right? Hydrogens are missing. Well, remember when you have an acid and a base react, what do you get? Get a salt and water. So we're going to get water over here.
So it's A plus B over and then the arrow and then C and D and then you like switch them.
Oh, you mean a double replacement? It's an acid-base reaction, yeah. Yeah, here's the base, here's the acid, here's the salt. Calcium here, nitrate here. And then the rest of it makes water. Yep, it's a double replacement acid-base reaction. So we need to balance this thing first, right? If we have 2 hydroxyls, we need 2 hydrogens to make up the difference. Because if you have a hydroxyl here, how many hydrogens do you need? You need 1 there and 1 there, right, to make water. So that means we definitely need 2 of those hydrogens. And that gives us 2 nitrates over here. So that's all we need, just that 2 in front of the nitric acid. Now, if you want to, you can do the budget, but you'll come up with the same answer. Okay, now we want to find out, what was the question again? How many grams of this one? Okay, so we got to convert this to moles, then go to that moles, and then go to grams. So 6.33 grams converted to moles. We need the molar mass of calcium hydroxide. Calcium is 40.08. 40.08 grams per mole. And we got 2 oxygens. So 2 times 16 is 32. And we got 2 hydrogens, which is 2.02. Right. There, 1, 2 plus 8, 10, carry the 1, and 4, and 74.10. Okay, divide that into 6.33. Let's see, that's 8.54 times 10⁻²moles of calcium hydroxide. Okay,
How many moles of calcium nitrate is that? Exactly the same. Right, 1 to 1. Okay. So now we can convert that to grams. We just need the molar mass of calcium nitrate. Okay, calcium was 40.08. Just like before, and 2 nitrogens. Right, nitrogen is 14.01. So we need 2 times 14.01 for the nitrogens and 6 oxygens. Right, I want to use my calculator for this one. And 28.02. And 6 times 16. 96. Yeah, 96. Plus. So that's 164.10. Right, so now we're going to take this and convert it to grams. Moles on the bottom, grams on the top. And that's 164.10 grams per mole. Okay. So that's times that value. And I get 14.0 grams of calcium nitrate on board. B. B is your answer.
Where are you getting the 10⁻²? Was it, did it just pop up in the calculator?
Yeah. Mhm.
Okay.
If you've got your set to standard notation, it'll probably 0.0854. I like to have, I keep mine set on scientific notation.
What is it? 8.54
Times 10⁻².
But you did that because you went 8.33 divided.
Oh, yeah, 6.33 divided by 74.1.
So I just got the decimal, but then I would go over to make it.
You don't have to make it, you don't have to make it this way. Yours probably reads 0.0854. Okay.
But if I wanted to, I could just go over twice and that's how I would get the -2.
Uh-huh.
Oh, that.
Yep. Or you can set your calculator. I don't know. Can you do that on your calculator?
I don't know what you're talking
Okay. It may not have scientific notation.
So mine gives me 8.54 with a bunch of numbers and 10 to the -2. So I can just use the first three.
Yeah, you'll want to round to that position. I'm not sure what,
It's, if you do,
5.4,
it's 4.
5.4251.
Yeah.
Yeah. So you just drop everything else and leave it there.
Because we're just, it's a kind of like significant figure, just
Mhm.
2 decimal places over.
Yeah. I got 3 decimal places here, so I kept 3 here.
This.
Okay. 52. For the reaction, P4O10 plus water yields H3PO4. What mass of P4O10 must be consumed if 3.71 times 10 to the 23rd molecules of water are consumed? All right. So what we're trying to do here,
P4O10 plus water yields H3PO4,
phosphoric acid.
and this, oh, good, they balanced it for us. Okay. So we're looking for the mass. Yeah, the mass of P4O10 in grams. If we start off with 3.71 times 10 to the 23rd molecules of water. So the only purpose that this serves is to keep the equation balanced. We're only interested in this side right here. So we need moles. Actually, we could put molecules over here first and then convert it to moles. It doesn't matter either way. We can do moles first, or we can convert molecules to this. I'd like to get moles because it'd be a smaller number and easier to handle. All right, so we have 6.022 times 10 to the 23rd molecules per mole. So we divide this into that. 3.71 x.23 and 6.022 x.23 divide. And that's 0.6161 moles of water. Now we can convert moles of water to moles of P4O10. We just need the coefficients, right? 6 here, 1 there. Divide by 6. So I get 0.1027 moles of P4O10. Now we need to convert to grams. Right. Moles in the bottom to cancel those moles, and leaves us with grams. So what's the molar mass of P4O10? 4 times 30.97 for phosphorus, and then 10 times 16 for oxygen. 30.97. I get 283.88 grams per mole is the molar mass of this compound. Okay, times 0.1027. And let's see, we get 29.1 grams of P4O10. B is your answer. My goodness, we're still in chapter 3. Hope chapter 4 is short. See if we've already done one like this before. 5.95 gram sample of silver nitrate reacted with barium chloride according to the equation to give 3.17 grams of silver chloride. What's the percent yield? Okay. Oh, this one's pretty quick. It just looks bad. All right. Well, we do have to do a little work. So let's put the silver nitrate, which is soluble, plus barium chloride, which is soluble. And then we react them and we get 2 silver chloride solid, drops out of solution. And then barium nitrate, which is soluble. Okay, is that balanced? Yeah, that's balanced. Okay, so 5.95 grams of silver nitrate, 5.95 grams of silver nitrate are reacted with barium chloride to give an actual output of 3.17 grams of silver chloride. 3.17 grams. Right. This is actual. We need to find the theoretical. So we got to go from this one to moles to grams and ratio those. Right. So this is going to be molar mass of silver nitrate. 107.87 for silver. Nitrogen is 14.01. 3 times 16 is 48. Right, so we get 8, 8, 12, 19, carry the 1, 6, 1, 169.88. Divided into 5.95. And that gives us 3.50 times 10 to the minus 2 moles of silver nitrate. Then we convert that to silver chloride. Silver nitrate on the bottom, silver chloride on the top. And the ratio is 2 to 2, right? So it's exactly the same, right? 1 to 1. 3.50 times 10 to the minus 2 moles of silver chloride. Now we want to convert that to mass. Moles on the bottom, grams on the top. That's the moles cancel. All right, silver chloride, what's that? Silver is 107.87. We found that one already. Chloride is 35.45. Add those together. 2, 1, 13, carry the 1. Yeah, carry the 4. 143.32. Okay. 1. So I get 5.02 grams theoretical. Right? Versus actual 3.17. So the percent yield is the easy part. 3.17 grams divided by 5.02 grams times 100. And I get 63.1%, which is D. Did I lose you? Handling fast.
There's a lot still left in chapter 3.
So you need to find the theoretical and you need to find the actual by the theoretical,
Correct.
then times by 100 to get the percent.
Percent, yeah, percent yield. This is what we would expect, and this is what we actually got. Let's see, 59. What's the mass of it? All right, 59, you have to actually calculate, you have to find out which one is limiting. So I guess we need to do that one. All right, so the balanced equation is methane plus chlorine gas yields carbon tetrachloride plus hydrogen chloride. This is completely gas reaction. Okay, what mass of carbon tetrachloride is formed? Right? Mass formed if 1.2 moles of methane, 1.2 moles of methane is reacted with 1.11 moles of chlorine. All right, we're going to reason this one. The ratio is 1 mole of this, 4 moles of that. Right? So if we need 4 of these, if that represents 4, what is 1? Right? 4 into, that's about 0.2. No, it's like that. 0.2, 0.3. It's about 0.27. Right? That represents 1. If this is 4, then that's 1. This is going to be excess. Right? We're going to run out of that one. So this is where we go for our calculation. 1.11 moles of chlorine. Now we're going to convert that to carbon tetrachloride. Ratio is 1 of these for 4 of those. So I guess I'll actually get the I'll get to the true value here.
That was close.
0.278 moles of carbon tetrachloride. Now we can convert that mole from the bottom, but I just moved this one from here over here. So what's the molar mass of carbon tetrachloride? Well, carbon's 12.01 and 3545 times 4 is the chlorines. Well, 0.01 added that. So I get 153.81 times 0.278 is 42.8 grams of carbon tetrachloride. 42.7, close. Rounding error.
What did you, like, what? did
Oh,
you divide
this-
with?
This is over here like that.
Okay,
So it would be this one times that.
They're both in the numerator.
okay, so you just times it.
Yeah, yeah, I had to move it over here because it was going behind the shades. That's why I put this dot here. That means multiply this thing times that. Okay. 59.
My goodness, is this ever gonna end? How many more do we have?
A lot.
Really?
Of just chapter 3.
It's 72.
Yeah, it is at 72.
And then we get into 4.
Actually. 74, and then we get into 4.
All right, let me see. Do we need to stop on this one? Which of the following statements is always true concerning reactions represented by the following balanced equation? We have equal masses. Okay.
Okay, 2 times C2H6, which is ethane, plus 7 oxygen, so we're gonna burn ethane. Yields carbon dioxide and water. 6 waters. And 4 carbon dioxide. Okay. If we have equal masses of C2H6 and O2, there's no limiting reactant. Well, what's the molar mass of each one? Let's do that. So 2 times 12.01 plus 6 times 1.01. Right. That will be the molar mass for ethane. .08 grams per mole. Right, so this is 30.08 grams per mole. And then the mass of oxygen is just 2 times 16, which is 32 grams per mole. Okay, we have equal masses of this and this. There's no limiting reactant. Equal masses would be like, and the ratio is moles to moles. We need 7 of these for 2 of those. So if we have equal masses, this one's gonna run out. It's not enough. All right, so A is false. How about B? If we have an equal number of moles of C2H6 and O2, there's no limiting the reactant. If we have equal moles, say we have 2 moles of this and 2 moles of that, then that one's going to run out because you don't have enough. Okay, so this was false also. If we have more mass of C2H6 than O2, then O2 must be limiting. More mass of this one. So if we have X grams here, it's greater than Y grams here. Let's see. 2 moles of this would be 60. And 7 moles of this would be 14. And 121 is 22. Yeah, that'll be that many grams.
Right? So now if we have more mass of C2H6, O2 must be limiting. We have 7 times 32. I think 14. 14, 1, 21, 22, that's right. That's if we have, this is mole to mole ratio, 2 to 7. This is mass to mass ratio, 60 to 224. Okay. If we have more mass of C2H6, then O2 must be limited. We have more mass of this one. Yeah. Yeah, if we have more mass, yeah, okay. You know, I think that's worded wrong. If we have more mass of C2H6 than what? It doesn't say more than what, does it? I think what it meant to say was more mass of C2H6 than O2. Then O2 would be limiting, and that would be true. Yeah. But that's the only way that C makes sense. If we have more mass of O2, then C2H6 must be limited. Well, yeah. I think the wording is bad on that one. But that's how I compared them. These ratios are stoichiometric. These masses are stoichiometric. Based on those values, right? 2 times that, 7 times that. That gives us the mass ratio for stoichiometric mixture. And then you can compare the rest of them. Okay. 62. Okay, I got about a half hour before I got split. So I don't know what I'm gonna do.
Possible if we continue to review next Tuesday and test Thursday.
Let me see. I got another buffer built in here, but it's after exam 3.
Could we just move it up and then push back?
Let me think. Tuesday and then move. What did that do for the rest of it? I move this one. That one. That one. I'm looking at the labs too, because you need chapter 5 in order to do Boyle's law. We'd have to move the lab too.
I don't think we had a lab for next Tuesday.
No, we don't.
So then that would give us plenty of time and we could just pretend that we had a lab and then continue the lecture over.
Or would it be possible to skip the rest of 3 and go on 4?
Yeah, we could do that.
And then you can go back and put the rest of 3 in if you needed to.
Yeah, we could do that.
Because 4, I mean.
Yeah, let's get 4 out of the way. Yeah, let's do that. Because all of these things are explained in the worked problems. Right. Okay, so that's what we're gonna do. We'll get this out of the way. I hesitate to mess with the schedule too much because the labs depend on it also. Let's see, an unknown substance dissolves readily in water but not in benzene. Molecules of what type are present in the substance? If it dissolves in water and not in benzene, what characteristics of the solvent would facilitate the dissolution in water but not benzene? And that has to do with polarity. Because if you have water as your solvent, it's polar. And you have benzene as a solvent, it's nonpolar. And which one would X dissolve in best? Well, it says readily in water. That means this has to be polar in order to dissolve. It won't dissolve in benzene. So B, it has to be polar. The solute has to be polar in order to dissolve.
Right? It's hydrophilic. It likes water.
Five. Which of the following is not a strong base? Okay, strong bases are made from alkali metals. All the alkali metals make strong hydroxides, which is a base. And alkaline earths make strong bases too, right? Calcium, magnesium, beryllium, all those make strong bases, right? So which one of these is not a strong base? Well, process of elimination, I mean, calcium, potassium, lithium, strontium is an alkaline earth, right? Those are all strong bases. Process of elimination says ammonia is not a strong base, and that's true. Right? We'll prove it later. Let's see. I don't know if we do it this semester, maybe next semester. We'll prove it. It's a weak base.
Next semester.
Yeah. Oh, wait a minute. This is 101, so it'd be 102.
Kim wanted to.
Yeah, that's what I mean. So C is the answer for 5. How about 6? Which of the following is paired incorrectly? All right. H2SO4, is that a strong acid? Oh, yeah. Well, technically, it's a strong acid for the first proton. When it goes like this, SO4, it's going to yield 1 proton plus HSO4 minus. That's the strong acid part. Then this one would go, and we'll learn this when we get to acids and bases. This one would go again and dissociate that other one. That's the weak acid. This is the strong acid part. So technically, it's a strong acid. HNO3, is that a weak acid? Nope. Nitric acid is strong. It's bad. I used to, before we could get pure acids from a supplier, right? What they call them, analytical grade. We had to distill them ourselves. So I'd pour the acid into the distill and heat it up, and it's distill over. And one time I was pouring it in, and I had a lab coat and I had gloves on. There was a gap right here. I poured it in there and it vapor locked and burped on me. And I got acid here. I had eye protection and, you know, like that. So the only place it got was right there on my wrist, and it turned brown. That's what nitric acid does to your skin. Right. I washed it off and it eventually behaved itself. But that's the bad one. Nitric acid is a strong acid. The rest of them are correct. How about 7? The man who discovered essential nature of acids through solution conductivity studies. All right, who worked on acids? That's Arrhenius. I don't think we covered that in class. Not in lecture. That would be from your textbook. Yeah. Arrhenius is the acid man. He did a whole bunch of other stuff, and we'll learn about him later, but that was one significant. Okay, 9. 16.4 grams of HF. 16.4 grams of HF is dissolved in water to give 2 times 10 to the second milliliters. 2 milliliters. What's the concentration in molarity? Well, we need 2 things. We can convert that to moles. Right? Because molarity is moles per unit volume, and volume has to be in liters.
Alright, so this is 200 milliliters, right? So that would be 0.2. Let's see, 0.20 liters. So there's our volume. Now we need moles. What's HF? Well, 1.01 plus 19, I believe. Yeah. So that's 20.01. We divide that into 16.4. So that's 0.82 moles. 82 divided by 0.2. So I get 4 molar. Up rounded off, 4.1, excuse me. 2 significant figures. There you go. Moles,
Why is it in?
that's just convention.
So to get the milliliters to liter, you just divide.
Well, I converted it to standard notation so that I could move the decimal 1, 2, 3 to get liters. Because there are 1,000 milliliters in a liter, you have to move it 3 places. You could go in and do like this, say, okay, milliliters and liters. 1,000 milliliters per liter, and divide that into that, you come up with the same number. Whichever suits your fancy. I've been doing a lot of this stuff in my head for so long, I don't think that there are other people that might need to catch up. All right, 14. What mass of calcium chloride is needed to prepare 3.95 liters of 1.49 molar solution? Right, go back to the formula. And we're looking for mass of calcium chloride. Well, we don't have mass in that formula, but we do have moles. So we can solve for moles. N equals molarity times volume. So we can find out how many moles of calcium chloride are needed. And then we can convert that to mass. So let's see, 3.950 is molarity. Right? And then volume in, oh, excuse me, that's liters. I'll just put liters here. And then molarity, I'll put over here. 1.49 molar. There we go. So 3.95 times 1.49 is 5.89 moles. So now we need to convert that to grams of calcium chloride. So calcium is 40.08. And 2 chlorines, right? Yeah, 2 chlorines. 35, 45. And 40.08. That's 110.98. That's the molar mass of calcium chloride. Okay, times 5.89. So you're going to need 60. Wait a minute. No, 654 grams of calcium chloride. Rounded off, 653. Rounding error. Okay. Let's see, 14, 16. We need to stop here. What mass of solute is contained in 250 milliliters? I don't think we need to stop on that one. You just use the same formula. Solve for what you need.
Right? We can't get mass from the molarity, but we can get moles. Then you convert moles of ammonium chloride.
So you're gonna have to say, this, well, 60. You're gonna have to say ammonium chloride. That formula. You're gonna have to calculate the molar mass of this one in order to get, let's see, we're looking for moles. Moles equals molarity times volume, and we need molarity. We got it, 0.838 molar. Yeah, and then volume is 256 milliliters, which is 0.256 liters. That gives you moles, then you convert moles. We could go ahead and do it out here. Like this. This would be moles. In grams, and you just need molar mass of ammonium chloride, and that'll give you your answer.
So you times these two.
Yeah, times those to give you moles, and I just went ahead and tacked this on the end because you're gonna cancel moles, and leave you with grams. And you need molar mass of this compound to fit right here. All right. 17. Let's see if we need to stop here.
74.28 gram sample of barium hydroxide is dissolved in enough water to make 2.45 liter solution. How many milliliters of this solution must be diluted with water? Okay, this is the dilution problem. So we have 74.28 grams of barium hydroxide. Okay, dissolved in enough water to make 2.45 liters of solution. So we're gonna need moles of this, grams, moles. What's the molar mass of barium hydroxide? Barium is 137.33. 2 oxygens is 32. 2 hydrogens is 2.02. So we add those together. And for 11, 167, 171.35. Divided into 74.28. That's 0.4335 moles of barium hydroxide. Okay, we're going to dissolve that in enough 0.4335 moles per how many liters? 2.450. 2.450 liters. So that'll give you the molarity of the concentrated solution, which is 0.1769 molar. Now, this is the concentrated solution, and the question is, how many milliliters of that solution do you have to dilute in a liter to make 0.1 molar barium hydroxide? So this is going to be the molarity of the concentrated. The molarity of the dilute is 0.100. Okay. The volume of the dilute is 1 liter. So the question is, what's the volume of the concentrated? Right. So we have M1V1 equals M1V2 or MC, VC equals MD BD, concentrated dilute. So we're looking for this one right here, VC equals MD times VD over MC. So if we just put those, now we can plug the numbers in because we got it arranged correctly. So this one is 0.100. Volume of dilute is 1. And then this one is on the bottom, 0.1769. And this is going to be in liters because that volume is liters. And our answer is in milliliters. So we're going to have to convert once we get the answer. So we got 0.1 in the numerator and 0.1769 in the denominator. This is 0.565 liters or 56.5 or 57 milliliters. Let's see, wait a minute. No, 565 milliliters, 3 places. That's A. Okay. Okay, I'm gonna skip 18. That's simple. 28. Oh, okay, now we're gonna identify reactions. Still right? Okay. $28. Okay. We've got these two equations. And we have to pick from A through E what they are. Okay, look at the first one. ZnBr2 and AgNO3 yields. So that's a precipitation reaction. Why? Because you've got two solutions on the reaction side and a solid on the product side. It's a double exchange, but it's also a precipitation reaction. Now, is it an oxidation reaction? We know it's C, right? C is guaranteed. But is it oxidation reduction? Because that would make it D. It's not an acid base. Right? Neither one of those are an acid or a base. So it can't be B. So what we have to do is say, is it A? And what you have to do then, well, in addition to saying both of them are the same type of reaction, both of them are precipitation reactions, yes. Then you look at the oxidation states for each one, right? Z and Br, 2. That means this is a 2+. Br is a -1. Okay. Silver nitrate. Silver is a +1 and nitrate is minus. Nitrate's the same on both sides, so it's not going to change. Silver bromide on the other side, right? -1 +1. That didn't change. How about the one with zinc in it? ZnNO3. ZnNO3 2. This is a minus, so that's a +2, right? That one didn't change, right? So it can't be oxidation reduction. We had no transfer of electrons. The only possible explanation is precipitation out of those that were given. Now about 29, all of the following reactions. All right. Notice, remember the little trick. If you've got an element on one side and it ends up in a compound on the other, whether it's starting as an element or it ends as an element, if it's in a compound on one side, element on the other, that is definitely oxidation reduction. Right. Aluminum and bromine make aluminum bromide. There you go. Silver 1 oxide. Let's see. No, silver oxide, because it's a fixed charge. Yields silver and oxygen. Right, there you go, elements. And methane and oxygen. Well, you can use that trick, or any combustion reaction is oxidation reduction. Right. But it says all of the following reactions. So only one of them is a combustion. That means you can't claim combustion for all of them. But you can claim oxidation reduction for every one of those. That's why A is the answer to 29. Kind of tricky. 32. Which of the following salts is insoluble in water? All right, for this one, you have to look it up. All right, just look at your scale here. And I'm sorry. Yes. Yeah, anything that's in the review document will also be on the test. So any of these pages, that page. The polyatomic ions, the periodic table, and that chart will be on the test.
And that chart, anything in the gray is
Insoluble.
insoluble. Which
Right.
means
It precipitates, or it doesn't go into solution, depending on if you have a double replacement reaction. And one of the products is grayed out, then that precipitates. If you take the solid and you try to put it in water, then you can see if it's going to go or not.
Yes.
Look each one of those up. Or if you know the rules, like I had to memorize the rules, all of those are soluble. Every one of them. That's why E is the answer. All right, 37. Okay, consider an aqueous solution of calcium nitrate added to an aqueous solution of sodium phosphate.
Calcium nitrate added to sodium phosphate.
And then what's the formula of the solid formed in the reaction? In this case, all you need is to know that it's a double replacement. So you take this cation, combine it with that anion, and see if it's soluble. Yeah, all nitrates are soluble.
Right, so this one is not a precipitate. Right, it's aqueous. But if you take calcium and combine it with phosphate,
You find that it's insoluble. That's Ca3PO4 taken twice. C. Wait a minute. Oh, that's tricky. Look closely. PO3 for D. Right. That's not anywhere in here. This is PO4. Phosphite is PO3. Phosphate is PO4. Ooh, that's sneaky. Okay. 38. Let's see, is it? Yeah, 38 is based upon that blurb right up there at the top. Aqueous solutions of barium chloride and silver nitrate are mixed, form solid silver chloride and barium nitrate. Okay, then it says the balanced molecular equation contains which of the following terms? So barium chloride,
aqueous, and silver nitrate, aqueous. Both of these are soluble. So double replacement says silver is going to combine with the chlorine and make a solid. And the barium combined with the nitrate is soluble. Okay,
but we need to balance it.
right, there are two nitrates on that side. We need two on this side. Now we need two silvers over here, two chlorines. Oops, that's a 2. This is a 2 plus minus 1.
Okay, so that's balanced. So the balanced molecular equation, which is this one, contains which of the following terms? Well, yeah, we're including coefficients. So A can't be right. B is correct. B is correct. How about the complete ionic equation?
The complete ionic equation takes these and separates them into their true ions forms in solution. And notice when this breaks apart, you get 2 chlorines or 2 chlorides. This has 2 silvers and solution and 2 nitrates in solution. Then we get this precipitate, which is not separated. Hang on to that one. And then we get a barium 2 plus in aqueous solution and 2 nitrates. Oops. Do that. 2 nitrates. Okay. So which one of those are true? Let's see. A is not true.
B is not true, C is true. 2 silver ions. Okay, and then the net ionic equation would mean that we cancel the spectators. Right, silver and chlorine have to stay here. But barium's the same on both sides. Nitrate's the same on both sides. So what we have left over is 2Cl minus plus 2Ag plus yields 2 silver chloride solid. But notice 2, 2, and 2 can be reduced further. All right, so we make that a 1, a 1, and a 1. And then we look for it. Silver aqueous, that's true. Barium's not there, nitrate's not there, hydrogen never was there. Silver chloride is not aqueous, solid. All right, so the only one that fits is the Ag plus. And the reason it doesn't have a 2 in front of it is because once we got the net equation, we find that it's 2, 2, 2, and the ratio is 1, 1, 1. All right, 45. All right. When solutions of strontium chloride and sodium sulfate react, which of the following is a spectator ion? All right, so strontium chloride, SrCl. Strontium is an alkaline earth. All right, so it's a +2. That means we need 2 of those. And that's aqueous. In fact, we're told it is. Sodium sulfate. Sodium sulfate. This is a 2-, that's a 1+, so we need 2 of those. Aqueous. All right, when they react, strontium and sulfate, well, sodium chloride, of course, is soluble. We know that. And then strontium sulfate is insoluble. We just look it up. Okay, we don't have to balance it. What we have to do is say, which of the following is a spectator? Strontium's not a spectator because it forms the precipitate. Sulfate is not a spectator because it forms a sulfate, the solid. Okay, so what do we have left? We have chlorides and we have sodium ions. That are the spectators. Right, so are those choices? B is chloride, C is sodium ions. So E, 2 of these are spectators. Okay. 50. Let's see if we need to stop on that. Okay, next time I do this course, I need to build a buffer into this chapter of this test.
And don't think that we can go over it some more Tuesday.
No, we're gonna have an exam on Tuesday. Anything that's missing is in the handwritten. What mass of sodium hydroxide is required to react exactly with 25 milliliters of 2.7? Okay, this is a titration, a neutralization reaction. So if we have sodium hydroxide in solution and sulfuric acid in solution, they're going to produce, they're going to produce sodium sulfate in solution plus water. Okay, so we need to balance that. We need 2 sodiums here. And that's it. Because 2 hydroxyls and 2 hydrogens make there 2 waters. Now it's balanced. All right, if we have 25 milliliters of sulfuric acid, 2.7, 25 milliliters of 2.7, molar. Then what we're looking for is what mass of sodium hydroxide. Oops. Okay, so we can determine how many moles of sodium hydroxide are required.
We know that if we multiply these together, we get
2.7 times 25. Why don't we go ahead and convert these to liters, because we're gonna need moles anyway. So 25 milliliters equals 0.025 liters. 0.025 times 2.7 is 6.75 times 10 to the minus 2 moles of H2SO4. And then we're going to convert that to sodium hydroxide. Okay, what's the ratio? 1 to 2. 2 here, 1 there. So 2 times this equals 0.135 moles of sodium hydroxide. Now we can convert that to mass. We just need 23 sodium, yep, 23, 1 oxygen, and 1 hydrogen. And so that's 1, 0, 10, 4, 40.01 times 0.35, which is 5.40 grams. 5.4. Yeah, 2 significant figures. Okay. We done? Nope. Get some more. 52. Which of the following does nitrogen have an oxidation state of +4? All right. A, B, C, D, and E. Yeah. So we got HNO3, NO2. These are oxidation states. These are not charges. We've got several covalent compounds here. Or polyatomic ions. I don't know if you caught it, but polyatomic ions are covalent. They're covalently bound. So even if they're in an ionic compound, the polyatomic is covalently bound unit. That's why it has that charge is assigned to the whole thing. Okay, so what's the oxidation state here? Well, -2 there. So that's a -6, and this is a +1. So those together are -5. That means this is +5. Nitrogen has to be +5 to balance it. This is -2, so that's -4 total. This is +4. Right? All right, we were looking for +4, weren't we? Okay, we found it. We can calculate the rest of them, like -2 here, this is +1. This is -1, this is +4, so it's +3, this is -3. Let's see if that adds up. Yeah. This is -2, so that's -4 total, +1. So that's -3 here, that's +3 there. So nitrogen can have a whole range of oxidation states. It's almost as full as carbon. Carbon can have oxidation states from +4 to -4 in one increment. So you can have 4 + 4 is 1 is 9. You can have 9 oxidation states. Oxidation state of iodine in this next one. (53) Oxidation state of IO3 minus, and we want iodine. So 3 times -2 is -6, but we want to hold one of them out for that charge. So we really only have to balance -5 with a +5. So +5 is the D. Because when we add everything up, it's got to be the charge on the polyatomic. Which of the following statements is not true? 55. When a metal reacts with a non-metal, an ionic compound is formed. Yep, that's true. B, a metal non-metal reaction can always be assumed to be an oxidation reduction reaction. Yeah, if it's elemental metal and elemental non-metal, it's oxidation reduction. Yeah. Two nonmetals can undergo an oxidation reduction reaction. Yeah. All we need is one example.
How about water?
Right, that's two nonmetals.
Okay, so that was true. How about D?
When two nonmetals react, the compound formed is ionic.
Oh. And we found our false one.
That's it.
56.
In the reaction, two calcium, oxygen yields calcium oxide. Which species is oxidized?
Okay. 2 calcium plus oxygen yields 2 calcium oxide. All right, this one's 0. This one's -2. This one's 0. This one's +2.
So oxidized oil rig, oxidation is loss. Which one lost electrons?
Calcium. To go from here, it's a loss of 2 electrons.
So calcium is oxidized. That's C.
All right. 57.
In this reaction, cesium plus chlorine yields cesium chloride. Chlorine is what?
All right. Cesium plus chlorine yields cesium chloride. Yeah, there are 2 of them. Okay. So this one's 0, that one's 0, this is -1, this is +2. So this cesium went over here, it lost 2 electrons per atom of cesium. This chlorine went over here, oops. Did it right? Nope, excuse me. That's wrong. +1. So they only lost 1 electron. Times 2 cesiums, that's 2 electrons. There you go. And this chlorine went over here and it gained 1 electron per chlorine times 2 chlorines equals 2 electrons. So this one was oxidized, this one was reduced. So in the reaction, chlorine, if it's reduced, it's the oxidizing agent. Or it promotes that reaction. Okay, let's see. Chlorine is B, the oxidizing agent. Yep, there it is. Okay. 61. All right. See. Really pushing it. Which of the following statements are true? Oxidation reduction cannot occur independently of each other. True. Accompany all chemical changes. False. C. Describe the loss and gain of electrons respectively. Yes. Oxidation is loss, reduction is gain. Results in a change in oxidation state of the species involved. Yes. So A, C, and D are all true. B is not. How many more we got? $63. Want to balance this one with the oxidation number method? Okay, Fe plus Br 2 yields Fe 3 plus Br minus. Okay, this one's 0, that one's 0. And Fe is going to have a loss 3 electrons per iron. And Br is going to have a gain of 1 electron per bromine. Okay, so how do we get that to balance? Well, we can't get 3 out of 2 and 1. We multiply 3 over here, then we're gonna take a fraction here. So what if we cross multiply? Say, let's make this 2 times 2 equals 6 electrons. And then multiply this one so we can get 6 electrons. We need 6 here, and we only need 3 here because that gives us 6 bromines. 6 bromines equals 6 electrons. Okay, so it's 2, 3, 2, and 6. 6 is the coefficient. Will be R minus. So how many we got? 1, 2, 3, 4. 4. Yeah, 4. There we go. It's this one, isn't it? 66. Spectator ions for the following. I'm not going to do that. We've done spectators already. Identify the precipitate formed if any of the following reactions in aqueous solution. All right, in this case, you just swap the cations and anions. Right? Ammonium nitrate is soluble. Iron 2 carbonate is insoluble. Right, so it'd be Fe. Let's see, this is 68. Fe2 plus, right? Yeah, and carbonates 2 minus. So it'd just be 1 iron and 1 carbonate. And this is a solid. So that's the answer is B. Which of the following does nitrogen have the highest oxidation state? Go back to the one we did before. It's the same list and just figure out which one's which. The highest oxidation state should be A. Which of the following does iodine have the lowest oxidation state? All right, 71. All right, lithium iodate. Now this one's easy, that's a 0. Ammonium iodide, this is +1, this is -1, all right, so this one beats out that one. This one's 0, that's -1. This one is +1, this one is -2, -6, +1. This is +5, so it's the highest. IO2, -2, -4 total, +4. Right. C, I2O, -2, this is +1. All right, so there it is. E, that's the lowest oxidation state. Oh, is that it? All right, about time.
But basically, if we just study everything that we just went over, we'll be okay. For the
Yeah.
exam.
And the ones that we missed, check them out on the work problems.